You good?
Okay.
No problem. We're going to finish off today's lesson. Today is going to be lots of practice with this. Right now, on Friday, I'm going to technically be finishing off the unit. It's a short unit. Monday is going to be a lesson on graphing tricks, which I could stick anywhere during the year. I stick it in this one because it's a short unit. Right now, I'm looking at your test being not this Friday, not the following Friday, but the first Monday of the final week before Christmas. If you know you're going to be away, and I think that works okay because I think, Mateo, you're away on the Tuesday, I think. So if you know, though, you're going to be away that week, you want to write it the previous Friday. You do not want to wait till after Christmas break. Okay? Let's look at this one here. It says a 3,000 Newton car. Now, I gave you this. Is that in kilograms? No. What units are it? In fact, what I just gave you was mg. I took the mass and I multiplied it by 9.8 already. I gave you the weight, not the mass. At rest, you guys all know that I tend to underline the word at rest. At the top of an incline 3 meters high and 30 meters long is released and rolls down the hill. What's its speed at the bottom if the average friction force is 200 newtons? Thank you. Hey, Nick, what's this question asking me to find? I gotta be fussy. What English word did they use? Did they use the word speed or did they use the word velocity? Say it again. Even that alone is a hint that suggests to me maybe I want to try a scalar approach. Okay? Is there a change in height in this question? I think so. Is there a change in speed in this question? So I'm already kind of leaning towards conservation of energy. I don't know that there's a yucky, curvy path, but when they start talking about average friction force, and I think I'm going to go with conservation of energy. G. Okay? I'm going to go like this. Kinetic initial plus potential initial equals kinetic final plus potential final plus heat. Wait a minute, Mr. Dewick. I didn't see them mentioning heat. Well, they did, sort of. Why did I include heat here? They're talking about friction. By the way, I think I could solve this all using kinematics by drawing a picture, by using friction as mu times the normal force. I don't know the normal friction. Of course it is. I could figure out the angle from 30 meters high and 30s long. I could go shift sine. I think it'd be shift sine. I could do all that. But the nice thing is I could also use a scalar approach, which is going to be much nicer. Are any of these zero? At rest? We're ending up at the bottom because we can put the ground wherever we want. So I'm going to get mgh initial, there's potential energy initial, minus heat equals a half mv final squared. Now, heat is not 200 because this is newtons. This is a force. How would I get the VF by itself? I think I'll divide by a half m and then square root. You okay with that? So let's write that. VF is going to be divide by 0.5 m. It's going to be a big square root. And I have mgh initial minus, and then I'm going to pause. How the heck could I write heat? Or how can I figure out heat? Heat is the work done by friction. So I think heat is going to be the force of friction times the distance that friction is acting for. Now, which distance am I going to use? I think friction is acting along the ramp, so I think I'm going to use the distance along the ramp. Am I going to use the 3 or the 30? I'm going to use the 30. You okay with that, Jeelan? So I'm going to argue this is going to be the force of friction times 30 times distance. It's going to be m. I don't know m. Well, wait a minute. What did I say this 3,000 was? Not m, but then you know what? Why don't I just put 3,000 in for mg, and then I'll times by h3 minus force of friction times the distance of friction. There's heat. Divided by 0.5 m. Oh, you know what? 3,000 divided by 9.8. That'll convert it back to kilograms, right? Okay. This is where a scalar approach shines. I could have done this using a vector approach by drawing a picture, by finding theta, by going winner minus loser. I could have done all of that. It would have been far more lines of work than this. 3,000, let's try that again, bracket, because it's a fraction, 3,000 times 3 minus 200 times 30, close bracket, divided by bracket, 0.5 times 3,000 divided by 9.8, square root of that. 4.4? 3? 4.43 meters per second. Little technical comment on ramps. You'll notice, although there is a normal force on a ramp, it doesn't show up in my work or energy equation, and that's because the normal force is always 90 degrees to the distance. Remember we said that work was force times distance times the cosine of theta if they were at angles, and the cosine of 90 is 0. So I wrote here, the normal force does no work because it's perpendicular to the ramp, perpendicular to the motion. So if the ramp is frictionless, energy is conserved. If we have friction, whatever left went into heat. The same argument actually applies to tension in a rope swing. Not if I'm raising it vertically. If I'm raising it vertically, tension is doing work because tension and the distance are in the same direction. But if I'm swinging this way, tension right now is pointing towards the center, but the distance is at a right angle. Tension right here is pointing straight up, but the distance I'm moving is this way. In fact, the distance I'm moving is always at a right angle to the rope. So, as long as the rope has no friction, energy will be conserved. In fact, the reason this pendulum, this little weight, is slowing down, it's losing almost all of its energy due to air resistance, bumping into air molecules. There's a bit of a problem. My hand is moving because I'm a human being, so I imagine I'm also absorbing or adding some energy. If I clamp this to a nice solid base, though, and if we had a really, really heavy pendulum, it'll swing for a long time. Pause the video. We're going to go off on a bit of a tangent. Put your pencils down. So the whole point of that rant was to really say, look, on a ramp, normal force does no work. On a rope swing, tension does no work if you're swinging. It means I can also analyze rope swings with the law of conservation of energy. Tarzan. Tarzan has a mass of 85 kilograms, and he runs at 6 meters per second. Don't write this down. We're imagining Tarzan is running along, and he's going to grab this rope swing. He's running at 6 meters per second. He's going to grab it, and he's going to swing up. Okay? I don't know if you've ever tried that with a rope swing. It's fun. Here's my question. Is there a change in height? Is there a change in speed? Is there a yucky, curvy path? I know what I'm thinking about using. He grabs onto a vine. He swings until he stops. Probably that there is going to be important. I'll use that. says write a work energy equation. Although it says write a work equation, I'm going to use conservation of energy. I'm going to write KE initial plus PE initial equals KE final plus PE final. And they don't want me to include any friction between the rope and between the vine and the tree branch. So, okay. Are any of these 0? Are any of these 0? Okay, stops. Yes? What else did you say? Does he start on the ground? Well, it all depends because the vine is here and Tarzan's feet are here. But wait a minute. Remember in that skateboard app I showed you, we can put the height of 0 wherever we want to make it most convenient. So, hey, it's most convenient if I put the height of 0 there. In fact, let's even put a center of mass right there. So yeah, one of the nice things, because energy is a scalar, Prince Edward Island, please, not a real province. So I get a half mv initial squared equals mgh final. Oh, I noticed something else too. Mass cancels. What does that mean? Well, supposing this vine was infinitely strong. So let's remove the fact that it might snap. If Tantor the elephant came running along at 6 meters per second, he would swing to exactly the same height as Tarzan will. Okay? In our magic physics world where all the numbers work out nice. What are we trying to find? Oh. Divide by g. Final height is going to be vi squared. I think we're going to divide by g. And you could put a 0.5 on the top, or you could put a 1/2. Usually when I'm multiplying by 0.5, that's the same as dividing by 2. I'll just tuck that there because it looks prettier. I'm going to get 6 squared all over 2 times 9.8. 6 squared divided by 2 times 9.8. And I get 1.84 meters. I didn't grow up in Pitt Meadows. Is there a good rope swing somewhere over water that you all know about that exists or not? You guys don't have one? Okay. Out in Hope, there used to be a good one on Kakawa Lake. A really good one where they'd even mounted a good water ski handle on the rope, and the water there was about 50 feet deep, so it was nice and safe. As safe as a rope swing is ever going to be. Nothing here? Okay, you guys missed out. Oh, there is one on L?
Yeah, but that's not the Meadows.
Okay. Okay. So you can try the physics with safety, but you can try the physics. Put your pencils down. So that little demonstration, I hope that convinces you. Energy work, just it's a scalar. It doesn't care about the path that you take. Energy is conserved. One more and we're done. Oh, roller coasters. I like this question. I like this question. I like this question. If the ramp is frictionless, it is. Write a work energy equation and find the speed at the bottom of the ramp. That's part A. Do you actually spill? Yeah. Oh, cool. I mean, that's oh, I feel so bad. Okay. What do they want me to find in part A? A speed. They didn't say velocity, they said speed. Nick, that already suggests a scalar approach. Shayna, is there a change in height in this question? Is there a change in speed in this question? Is there a yucky curvy path? I don't want to use a vector approach. Conservation of energy. So I'm going to start out KE initial plus PE initial equals KE final plus PE final. Initial plus initial equals final plus final. What you start with is what you end with. Hey Shane, are any of these 0? End up on the ground? I don't think anything else is. We didn't start at rest. We started 2 meters per second. I guess we just barely made it over the hill to get ready for the next hill, which happens in some roller coasters. Well, a half mv initial squared plus mg h initial equals a half m v final squared. Oh, cool. Shana, have you been on a roller coaster before? When you got on the roller coaster, before you got on, did they make you stand on a scale? Did they make... No? Do you know why? And even if we did have friction, as long as friction is pretty small, the mass will be negligible. Although, again, if you graph Americans and mass, that might change in the next few years because it seems to be going up. What am I trying to find, Shana? You could, right now, divide by 0.5 square root. I'm a math nerd. I'm going to clear fractions by going times by 2, times by 2, times by 2. That gets rid of those two halves. And I end up getting vi squared plus 2gh initial equals vf squared. I smile here because I've just derived vf squared equals vi squared plus 2ad, kind of along the way. And then how do I get rid of a squared? Square root. Alrighty. So the speed at the bottom is going to be 2 squared plus 2 times 9.8 times 10. Hey, I should be able to do this in my head. I think I can. 2 times 9.8 is 98, times 2 is 196 plus 4. It's going to be the square root of 200. That I can do in my head. Square root of 100 is 10. Square root of 2 is 1.414, so it's going to be 1.414 times 10. 14.14, right? Booyah! Square root of 2, that one I know. 14.1, you'll notice I was able even to go to 4 sig figs. Ooh, meters per second. That's the theoretical speed. Let's suppose we did this experiment. I do have a radar gun, and I'll let, if some of you want to bring it to Playland and actually measure some speeds, you can. Let's suppose we used a radar gun, and we got the speed to be 12 meters per second. Part B. Where'd the extra energy go? We're going to call it heat. Honestly, Hayden, really what I mean is we lost some to sound, we lost some to air friction, and we lost some to heat. But we're going to call it all heat. Pause for 1 second. So let's keep going. Now it's talking about heat. It's still a change in height, change in speed, yucky curvy path. So I'll go kinetic initial plus potential initial equals kinetic final plus potential final. But now it says find out how much energy we lost to heat. Okay. Derek, are any of these 0? Still the same. Final. I want to get the heat by itself. How do I get the heat by itself? Yeah. Subtract, sorry? Final kinetic energy. Nicole, I've said this before, I'll say it again. For some reason, I don't know why, on this specific question, which suggests you'll see something very similar to this in the future, kids divide. It drives me crazy. I don't know why. Because there's like a plus sign and a plus sign. Why would you? But they do. So I'm going to get this. The heat, I'll do that in red. Ooh, a heat color. Is your initial kinetic, your initial potential, how much energy you started with, minus how much energy was left for the object to move with. Whatever's left over must have gone into heat. It's going to be a half m v initial squared plus m g h initial minus a half m v final squared, where this time v final, instead of 14.1, what did I say? I've scrolled down. What did I say v final was in part B? Someone read for me, please. I've scrolled down. 12. Okay, here we go. The heat is going to be 0.5 times 1,000 times 2 squared plus 1,000 times 9.8 times 10 minus 0.5 times 1,000 times 12 squared. Yes, I think. And I get 28,000 joules. Anybody else? Someone tried? I see some of you nodding and you haven't even touched your calculator. I don't know. We're going to add a part C. I keep forgetting to add it to the actual lesson. Here's our part C. Find the average force of friction. Why did I say average force of friction, Renzo? Because since it's curvy, theta, the angle, is changing. And since friction was mu times the normal force, I don't know the normal force. Oh, but look, of course it is. Cos would be changing all the time. Friction would be changing all the time. So I can't find the force of friction at any one point without calculus. I could with calculus. But I can find the average force of friction. How? How? I'll give you a hint. It's going to use something I found in part B. Oh, this heat is the work done by friction. So I can say the work done by friction equals the force of friction times distance. How much work was, the force of friction is going to be the work divided by the distance. How much work was done? 28,000. And really, here's the key question, Cassidy. Which distance am I going to use? Yeah, the ramp length, because that's going to give me the length. It's actually an average length, but that'll go with the average force of friction. Okay. Oh, nice. Works out evenly. 1,600 newtons. Okay. I guess I could even find sort of an average coefficient of friction now. If I found an average normal force, what would the average normal force be? Well, if it's 10 high and 17.5 long, I could use shift sign, and I could find theta, and then I could say the average normal force would be mu cos, mg cos theta, and I could even find an average. I'm not sure if those would have any actual real-life meaning or not, though, Mateo. I'm just spitballing here. What's your homework? So you can try every question, except I'm going to even no longer nuke number 5. You can add it. You can just do it at the end of the homework if you want to. And then if you finish that, you're now capable of doing these questions here from the ultimate review. So if you want to jot these down underneath number 10 or on the top front of the lesson, but you can now do from the review, from the ultimate review, 1 to 3, 5, 6, 8, 9, 10, 12, 13, 17 with a star, 18 with a star. Those ones are tricky. 20, 21, 22, 25, 26, 29, 31, 32, 33, 34, 35, 36, and 39. That's if you finish the homework today, because the test isn't that far away. If you want to get a head start on the ultimate review, you can also do those questions as well. Okay? Yep. Pardon me? Yeah. If you want to take a picture of it, that'd be a smart way to do it too. I have to photobomb it, right? Of course. Okay, I'm just going to save the video here. Give me 1 second. Stop.